Hello everyone. Today I'm gonna explain the main ideas present in the proof of Godel's first and second incompleteness theorems. These theorems are very important for mathematicians in general and for logicians in particular. However, their proof can be hard to understand. My goal with this video is to make the topic a little bit more accessible. The video will be divided in 7 parts. In part 1, I'm going to explain what these theorems actually state. In part 2, I'm going to present the undecidable using natural language to build intuition. In part 3, I'm going to give a sketch or overview of the proof. In my opinion, these 3 parts are the most important. In parts 4, 5, and 6, I'm going to explain respectively Godel's encoding, recursive functions, and how to formalize the undecidable. Finally, on part 7, I'm gonna discuss very briefly why all formal systems are incomplete. Let's begin. Let's say that you want to prove theorems in number theory. First of all, you will need a formal language in which you can represent the natural numbers, their functions, and their relations, with especially one function in mind, the successor function. And, well, since the definition of the successor function are the piano axioms, you want to represent those as well. Once you have your formal language, you want to prove stuff. For that, you will need the definition of formal proof. You will need some rules of inference. You will need the axioms of logic, and you might want to add some additional axioms or axiom schemas. So you can add those as well. This will be your system. Now you would like your system to have certain properties. First of all, you would like it to be consistent. A system that is not consistent can prove both a formula and the negation of that formula. If your system uses classical logic, that means it will be able to prove absolutely every formula with no discernment whatsoever, so it will not be very useful. The second thing that you would like is for your system to be omega consistent. A system that is not omega consistent is one that can prove both that a property doesn't hold for all objects, and at the same time, for every single object, you can prove the property holds. So you are proving that something is not universal, and yet there is no counterexample. I want you to note that if a system is not consistent, it would also not be omega consistent. Because if a system is not consistent, it can prove everything, including that a certain property doesn't hold for all objects, but you can also prove that the property holds for every single object. The third thing that you would like your system to be is complete. You would like that if you take any formula, using your system you can either prove it or prove its negation. Godel's first incompleteness theorem says you cannot have all three. A system that is omega consistent will not be complete. Now, let's say that you wanted to prove that your system is consistent, but you don't want to use something outside the system. You don't want to create a larger system to prove that your system is consistent. You want to somehow encode the consistency of your system in a formula inside the system and then try to prove it. Godel's second incompleteness theorem says that if you do manage to do that, to get the consistency of the system as a formula inside the system, then you will not be able to prove that formula. So these are the first and second incompleteness theorems. Now let's us go a little bit more in how Godel proved them. And to do that, let's talk about the undecidable. Consider the following statement. There is no proof of P. Let's call the statement P. The negation of this statement, not P, will say there is a proof of P. Now let's us assume that using our system we proved P. Let's call the proof Q. By actually writing the proof, we just prove the statement Q is a proof of P. And also, there is a proof of P. So we also proved not P. We proved P and not P, the system cannot be consistent. Let's say instead that we proved not P first. We proved there is a proof of P. Now we have two cases. The first case is that we can actually write such proof of P. The second case is that, well, we proved there's a proof of P, but we cannot actually write down the proof. Let's analyze the first case. In that case, we will have a proof of P, and we will have a proof of not P. So it's a contradiction. The system cannot be consistent. I want to stop here for a minute to point something out, and is that if the system is consistent, then, because of what we just said, there is no proof of P. In other words, if the system is consistent, then P. So, if you were able to use the system to prove the statement the system is consistent, you could also prove P, and so the system will not be consistent. So, if the system is consistent, it can also not prove the system is consistent as a statement. Okay, let's just go back to case number 2, in which we just prove that there is a proof of P, but we cannot actually write down the proof. This system can be consistent, but it cannot be omega consistent. The reason is that there's a property, not being a proof of P, that you can prove for every single possible proof. If you take any given possible proof, you can prove that it is not a proof of P. However, you can also prove that this property is not universal, that there's a proof that will not hold it, because you just proved that there is a proof of P. And so, you prove that something is not universal and there's no counterexample, it cannot be omega consistent. This is an example of a self-reference causing a paradox. We have known since antiquity this problem with self-reference, and so mathematicians have tried to avoid it. The usual way is to make a distinction between statements about some objects and the objects themselves. For example, statements about natural numbers are not natural numbers. It was believed that this was enough to prevent self-reference. The key idea of Gödel's proof is that this is not possible because natural numbers can behave like statements about natural numbers, and relations between natural numbers can behave like relations between statements about natural numbers. How he did that? Well, let's just go then to part 3. Let's just talk a little bit more about what's inside our system. Inside the system, we have symbols. We can form finite sequences of those symbols. We will call them formulas. Within the formulas, there are like a special subset, which are what we are actually interested in. They are called well-formed formulas. They are formulas that are constructed according to certain rules, and instead of being just a random sequence of symbols. And besides formulas, we have sequences of formulas. And these sequences of formulas, there's also a special subset, which are the proofs. So a sequence of formulas can be a proof of some formula alpha using some premises, some set of premises gamma. Or it can be a formula, it can be a proof of alpha from no premises at all, just using the axioms. In this case, we will simply say it's a proof of alpha, and alpha will be a theorem. There's something very nice about logical systems, and is that there are algorithms that will let you decide these properties always in a finite number of steps. So, if you are given a formula and you want to see if it's a well-formed formula, you just have to do the algorithm, and always after a finite number of steps, you will know if it's a well-formed formula or not. The same thing happens with proofs. So, if you are given a proof, a sequence of formulas, and a formula, you can run an algorithm that will let you know if the sequence of formulas is a proof of the other formula. This was taken advantage of by Godel. First of all, he assigned to each symbol, formula, or sequence of formulas a different natural number. Then he defined something he called recursive functions. Recursive functions can be thought of as, by the way they are defined, as functions in which you decide the output by applying an algorithm to the inputs. And after a finite number of steps, you will get the output. So he took the algorithms in the system of logic, adapt them to work on natural numbers, and use them to define some recursive functions. Then he used those functions to define some relations between natural numbers that correspond to the relations between statements about natural numbers. For example, there was a property of natural numbers that correspond exactly to the property of being a well-formed formula. Or there's a relation between two natural numbers that corresponds exactly to the relation between a sequence of formulas and a formula of one being the proof of the other. By doing this, he proved that the system that you're going to use to do number theory is actually part of number theory. If you were to know all the ways in which natural numbers are related to one another, you will also know all the theorems of number theory. You'll just have to realize that something being a theorem, it's equivalent to a number being related in some way to some other numbers. This means that any system that you can use to do number theory, it's also talking about itself. is self-referential, and so it can have paradoxes like the undecidable I mentioned before. If you have followed me so far, I consider my goal satisfied. I don't care if you close the video right now or jump to the discussion at the end of the video. That being said, the proof is full of very clever tricks, and I would like to talk a little bit more about them, starting with Gödel's encoding. So let's just start. Gödel's encoding is the process by which he assigned natural numbers to symbols, formulas, and sequences of formulas. Let's just start with the symbols. First, he assigned natural numbers to the constants. Those will be the symbol for the negation, the symbol for the disjunction, the universal quantifier, the parentheses, the number 0, and the symbol for the successor function. He represented the rest of the natural numbers with the 0 and the successor. So he said 1 was the successor of 0, 2 was the successor of the successor of 0, 3 was the successor of the successor of the successor of 0, and so forth. To these symbols, he assigned the odd numbers equal or smaller than 13. Then, he assigned numbers to the variables. Since he based his system on the one in Principia Mathematica, variables had types. He had countably infinite variables of type 0, countably infinite variables of type 1, countably infinite variables of type 2, and so forth. One type for each natural number. He started with the variables of type 0. He assigned to those the prime numbers bigger than 13, ensuring that these numbers will be different to the numbers assigned to the constants. To the variables of type 1, he assigned the squares of the prime numbers bigger than 13, ensuring they will be different from the numbers assigned to variables of type 0 and to the constants. For variables of type 2, he assigned the cubes of the prime numbers bigger than 13, ensuring the numbers will be different than the ones assigned before, and so forth for every type. Next, he assigned numbers to sequences of natural numbers. He did it in the following manner. Let's take a sequence of natural numbers. Consider a prime factorization such that the coefficient of the nth prime is the nth element of the sequence. We will assign to the sequence the natural number that has that prime factorization. Note that if we have two different sequences of natural numbers, they will result in two different prime factorizations, and so they will be assigned different natural numbers. In this way, you can assign natural numbers to formulas because they are sequences of symbols, so you can simply substitute each symbol with their corresponding natural number, and you'll get a sequence of natural numbers that you can turn into a natural number. You can also do the same thing with sequences of formulas. You replace each formula with their natural number, and you get a sequence of natural numbers that you can then turn into a natural number. Note as well that if you turn a formula or a sequence of formulas into a sequence of natural numbers, the first element of the sequence will never be 0, and so they will be assigned an even number, which will make them different than the natural numbers assigned to symbols, that are all of them are odd. Okay, now let's just talk about recursive functions. Now let's talk about recursive functions. Recursive functions, most of them, are defined in terms of other recursive functions. The first way in which this is done is by function composition. If you have two or more recursive functions and you compose them together in some other function, then that other function would also be recursive. The second way of defining them, it's a little bit more complicated. Let's call it the recursion schema. And in order to explain it, I'm going to use something that didn't exist when Godel wrote down his paper. I'm going to use a Turing machine. So let's say that we have the formula, a function that would take m plus 1 inputs and will give a natural number as output. So let's just find the output of the inputs n0, n1, n2, n3, n4 until nm. This Turing machine will obviously start in a place on an infinite tape. The starting point, will have printed on it the number 0. To the right, there will be the number 1, to the right the number 2, to the right the number 3, and so forth, for all natural numbers. It doesn't matter what's on the left because this Turing machine only goes to the right. The initial state of the Turing machine will be the list of numbers n1, n2, n3, n4, n5 until nm. So all the inputs but the first. What about the first? What about n0? As you'll see later, n0 will tell us when to stop the machine. But for now, don't mind it. Now, the machine will start the computation. It will read the 0 from the tape, forget about it, and then, using its state, determine what to print on the tape. Let's call what it prints f of 0. If you forgive me abusing the language a little bit. Then the machine is going to move to the right. It's going to update its state. The new state is going to be f of 0 and all the original numbers of the initial state. n1, n2, n3, and so forth until nm. Then it's going to read the tape. It's going to read the number 1. And based on the number 1, f0 and the original list of the numbers from the initial state, it will decide on f of 1 and it will print it. Then it's going to move to the right, update its state. The new state is going to be the original list of numbers, f of 1, and that's it. It will forget about f of 0. Then it's going to read number 2. Based on the number 2 and f of 1 and the original list of numbers, is going to decide f of 2. Then going to move to the right, update its state to the original list of numbers and f of 2, and so forth, until it reads from the tape n0. Once it does that, well, it will take n0, f of n0 minus 1, and the original list of numbers, print f of n0, and then it will stop. The output of the recursive function will be f of n0. Again, forgive me for abusing language. Now, there's something that I haven't mentioned about the definition. I mentioned what's the initial state of the tape, of the Turing machine, when does it halt, how it decides on where to move, and how to update the state. But I've never told you how it decides what to print. Well, for that you will need two recursive functions. One recursive function g that will take m arguments. So when it starts, once it reads the 0 and forgets about it, Then it will take the original list of numbers n1, n2, n3, n4 until nm, put them as inputs to G, and the output would be F0, what it prints on the tape. You will also need another function, H, that takes n plus 2 arguments. And at any other step of the computation, you will take the number you just read from the tape, you will take F of the previous number on the tape and the original list of numbers, put them as inputs of H, and the output it will be what it will print on the tape. And G and H must be recursive functions. Okay, so we already know how to define recursive functions from other recursive functions, but where do we begin? What are the building blocks? The building blocks are the successor function, the constant functions, and right now we also include the projection function. Godel didn't include that one explicitly. He rather added a footnote saying that not all arguments need to be present, but never mind that. Recursive functions have a very special property, which is that if you take a recursive function, give it some inputs, and get m as an output, you can always prove from the axioms of number theory that m is the output of that function given those inputs. The idea is something like this. If you were to do an algorithm with pen and paper and get m as the result of that algorithm, and someone were to ask you to prove that if you run the algorithm you will get m, you'll just show them your work step by step, and that will prove that m is the result of running the algorithm. Let's just think of a specific function. Let's say that we have a function f, recursive, and when we put the input n, we will get the output m. If f was the result of composing h and g, both of them recursive functions, you'll have to prove something like this, that g of n is equal to a and h of a is equal to m. And you prove that by going to the definitions of g and h, and then proving that g of n is a and that h of a is m. Let's say that f was defined using the recursion schema. In that case, you will have to prove that the initial state in this Turing machine, as I explained it, will give right this, let's call this initial state the zeroth state. This zeroth state will result in a first state that will result in a second state that will result in a third state, and so forth until it gets to an nth state that will result in the machine printing m on the tape. And so we will know that the output of the function was m. And how do we prove that? Well, by going back to the definitions of the functions g and h recursive that we used to define this procedure. So we will do the process again with g and h, and again with the functions that define them, and again and again and again until we get to either the successor function or the constant functions. And then the proof is trivial. That is roughly how you prove that given certain inputs, a recursive function will give certain output. Godel, after he introduced the definition, of recursive function, he started defining a lot of them. He defined a function that will correspond to the logical operator not, the negation. He defined a function that will correspond to the logical connective and to the logical connective or. He created a recursive function that will check if there's a number smaller than certain bound that has certain property, a function that will check if all the numbers smaller than certain bound have a certain property. He created a recursive function that will return the smallest natural number that has certain property. He also created recursive functions that modified for the formulas. That is to say, if you take a formula, turn it into a natural number, you can put it in the recursive function, it will give you another natural number that you can turn back into the formula that you want. An example of this is a recursive function that will substitute free variables by something else in a formula. And he of course created formulas that would check the relations that I mentioned before. For example, there's a recursive function that will be whose output will be 0 if and only if the number that was given corresponds to a well-formed formula. It checks if it's a well-formed formula. And of course, there's also another one, that a recursive function that takes two numbers and the output will be 0 if and only if the first number corresponds to the proof of the formula corresponding to the second number. Basically, the recursive function checks if the first is a proof of the second. Then Godel defined what he called recursive relations in the following manner. Let's say that he wants to define some relation R between m natural numbers. In that case, he will take a recursive function phi that takes m natural numbers as inputs and will give an output. So if he has a list of m natural numbers and wants to see if R holds for them or not, he will feed them as inputs to phi and see the output. If the output is 0, then R holds for those natural numbers. If the output is not 0, then the negation of R holds for those natural numbers. Essentially, some numbers are related if and only if a recursive function says they do. Recursive relations have a very special property, and is that you can always prove from the axioms of number theory either R holds for certain numbers or that the negation of R holds for those numbers. You just have to prove that when you give those inputs, those numbers as inputs to phi, you'll have to prove that the output is 0 or prove that the output is not 0. And as we mentioned before, you can do that. With this, we have everything we need to formalize the undecidable. Okay, so before we had a recursive function that checks if a natural number n is the proof of some natural number m. Forgive me for abusing language. So we're going to define a recursive relation using the recursive function. We're going to call it npm. N is a proof of m. And remember, if n actually is a proof of m, we will be able to prove npm. If n is not a proof of m, we will be able to prove n, we will be able to prove the negation of n p m. Now we're gonna take the not operator, the negation operator, which is a recursive function. We're going to compose the two of them together, the recursive functions, and then we're going to use it to define the recursive relation n p bar m, or n is not a proof of m. So if n is not a proof of m, we will be able to prove n p bar m. If n is a proof of m, we will be able to prove the negation of n p bar m. Next, we will put a quantifier on the variable n. We're gonna get for all n p bar m. For all n is not a proof of m. Or said another way, there is no proof of m. Then we need to get this formula inside itself, replacing m. So we just say, okay, we'll just turn this formula into a number, let's call it p, and get it inside, and get for all n p bar p. So we're done, right? Well, not quite, because if you turn this into a number again, you will not get p, you will get q, a different number. The formula is not actually inside itself. To better appreciate this, let's just go back to natural language. Consider the statement P that says there is no proof of M. Now consider the statement Q that reads there is no proof of P. They are different. One has an M, the other has a P. The second statement, Q, is not actually P, is P substituted on itself, which is different than P. So we should have aimed for something completely different from the beginning. We should have been aiming for, we want for the statement R that reads, there is no proof of M substituted on itself. And so if we instead take the statement there is no proof of R substituted on itself, that statement is R substituted on itself. That statement is inside itself. Okay, so let's just go back. We have n p bar m. Remember that before I mentioned a recursive function that substituted free variables inside of formulas? Then we can use that to define a function that does something like this. If you take a formula and turn it into a number and feed it to that recursive function, the recursive function, you can think of it as turning it back into a formula, identifying the free variables, substituting them with the number, let's call it n, then turn all of that into a number, and that will be the output. So we're going to take this substitution function and compose it with and use function composition to obtain the following relation: n p hat m, which reads pretty much n is not a proof of m substituted on itself. So if n is not a proof of m after substitutes all its variables inside itself with m, then we will be able to prove n p hat m. If n is a proof of m after it substituted all its variables inside with m, then we will be able to prove the negation of n P hat M. Then we just quantified the variable n as before. So for all n P hat M. For all n is not a proof of m substituted on itself, or there is no proof of m substituted on itself. Let's just turn all of that into a number. Let's call it r and get it inside. So now we have for all n P hat r. There is no proof of r substituted on itself, which it's r substituted on itself. So let's us assume first that we just proved that we can write a proof of r. In that case, since we prove it for all n, we proved in particular, let's call that proof t. So since we prove it for all n, we proved in particular that t p hat r. However, since t is a proof of r, then we can also prove the negation of t p hat r. So we just got a contradiction. We proved by a formula and its negation. Okay, let's say instead that we proved the negation of r. Okay, we have two cases. That there's actually a proof of r, in which case we also have a contradiction. In the two previous and the system is not consistent, and remember, if a system is not consistent, it's also not omega consistent, or that there's actually no actual proof of r. In that case, for all n, since n is not a proof of r, then we can prove for every single n P hat r. In that case, the system cannot be omega consistent, because we proved that P hat r for every single n, and at the same time we proved that the negation that for all n P hat r. So the system cannot be omega consistent. And so this proves Godel's first incompleteness theorem. If the system is omega consistent, then it cannot be you cannot neither prove r nor prove the negation of r. Now let's also speak about the second incompleteness theorem. You might feel tempted to use some of these tricks to try to get the consistency of the system inside the system itself. Perhaps you want to take the axioms, turn it into numbers, and create a recursive function that will be zero if and only if the numbers it took form a consistent system, or something like that. If you want to create a recursive function or relation that will correspond to the system being consistent. If you were able to do that, you will not be able to use the system to prove that formula corresponding to that relation. The reason why is because all the proof that we did before, we can formalize inside the system using the consistency of the system as a premise. So if you are able to prove this formula you defined, this would lead you to proving r. In that case, the system will not be consistent. That will be the second incompleteness theorem. Okay, now I just want to discuss a bit about why did this happen, how we did we get here. So let's just go to part 7. Now, in his paper, Godel added a footnote saying, as will be shown in part 2 of this paper, the true reason for the incompleteness inherent in all formal systems of mathematics is that the formation of ever higher types can be continued into the transfinite, while in any formal system at most denumerably many of them are available. For it can be shown that the undecidable propositions constructed here become decidable whenever appropriate higher types are added. For example, the type omega to the system P. An analogous situation prevails for the axiom system of set theory. He never wrote the part 2 of this paper, but he did later wrote down a different paper in which he well reinstated that. He said, okay, if you have your system with certain types, you will have undecidables, but if you add an additional type, then these decidables will become decidable. However, you can use the same procedure to generate completely new undecidables. If this is true, then he could use the system P he used in the proof, added an additional type omega bigger than all the types he had before that were just natural numbers, and that should make R decidable. He never mentions anything about using the procedure again to generate another undecidable for this new system. In any case, he changed his mind later on. He added to the paper a note on August of 1963 saying the following. In consequences of later advances, in particular of the fact that due to A.M. Turing's work, a precise and unquestionably adequate definition of the general notion of formal system can now be given, a completely general version of theorems 6 and 11 is now possible. That is, it can be proved rigorously that in every consistent formal system that contains a certain amount of finitary number theory, there exist undecidable arithmetic propositions, and that, moreover, the consistency of any such system cannot be proved in the system. With a footnote saying, in my opinion, the term formal system or formalism should never be used for anything but this notion. In a lecture at Princeton, I suggested certain transfinite generalizations of formalisms, but these are something radically different from formal systems in the proper sense of the term, whose characteristic property is that reasoning in them, in principle, can be completely replaced by mechanical devices. The generalizations he mentioned are a system he proposed in which there are primitive symbols for each transfinite ordinal. For each ordinal. Now, he says, okay, I propose that, but that is not a formal system. So what is a formal system for him? A system in which everything can be checked by Turing machines. Now, it was proven after he published his paper that precisely what's computable by a Turing machine corresponds to certain recursive functions we now call general recursive functions. Now, the recursive functions used in the paper are actually a special case of those. Right now we call them primitive recursive functions that are a bit weaker. However, the Godel's proof can be generalized using general recursive functions instead of primitive recursive functions, and so cover every system that can be checked using Turing machines, because you can use the definition of those Turing machines to build the appropriate recursive functions and then create the undecidables. So, to summarize everything, you can use number theory to create computers. So if you want your system, to talk about the natural numbers, to be able to be completely run by computers, then that system is a special case of number theory, and therefore is self-referential, and therefore It has paradoxes, and therefore it's not complete, and therefore it cannot prove its own consistency. That's the conclusion. That's all for today. Thank you for listening.